There are many types of counters and numerous methods to construct them. In this figure here, I'm showing you three examples of three different counters with different functionalities. Here's one, here's another one, here's a third one. We can of course use Verilog's structural modeling to build these counters, or any counter that you might have on an counter. But as you might expect, it started to become a little bit on the tedious side. So in this video, we're less concerned about the design and the physical ANDs and multiplexers and little tiny gates that we put in of these counters. I'm more interested into describing them behaviorally using behavioral modeling. So I'll show you some sort of a recipe that describes any counter functionality you might need. And I will only consider synchronous counters so that I don't have any glitches. Because I'm going to show you a recipe of synchronous counters, this recipe follows the general synchronous systems that we've seen before. And of course, that means we can follow the guideline in our coding. And the guideline, if you remember, that we put the memory component separate from the next state logic, which is combinational logic, and then the output logic. Frankly speaking, we're probably going to just write this here, which is just a register. And we'll add the reset part to it, and then most of the time we're going to be just changing the next state logic and sometimes the output logic, because sometimes we want a different output of the counter than just the number that it's counting. So let's go to Vivado and just write some code to describe up counters, down counters, and maybe counters that can load. Okay, so now I'm in Vivado. I opened up a new module called up counter. In this module, I'll be building a counter that counts up, like 0, 1, 2, 3, all the way up. And the number of bits necessary or in that counter will be generalized or generic or parameterized, so that we can actually go from like 0. In this case, by default, I'm going to use 4 bits. That means it can go all the way to 15. And of course, when I instantiate this counter, I can change this number of bits. And of course, like any other synchronous system, it should take a clock. And usually I include a reset so that we have like a baseline to go to, which is a bunch of zeros, and the output of the counter in here. So how do we write code for this thing here? It's actually, I'm going to follow this particular synchronous logic here. So let me show you. So the first thing we need to do is, like we done before, it's actually, I'm going to say, okay, I need a register of the same size of the inputs and output, or the counter or the register. Okay, and I'm just going to give it the current value, qreg, and a next value in here. And of course, I'm going to separate the always statement for the synchronous part, which is the register, which is usually activated by the positive edge of the clock or the negative edge of the clock if you wanted to. And I'm going to do the reset as asynchronous, so it's going to be reset n, and then what we can do is begin and end, and it's as simple as asking, is the reset clicked or not clicked? And you're going to see that the qreg will have, with non-blocking assignment, it will be 0. And you can either do 0 or you can do like a bunch, and this is binary 0. It's the same thing. Okay, and then we have else, and then qreg will be the value that we decide that it's the next value in here. So what I have just described is actually this part as a reminder, and we decided that this will be the qnext and this will be the qreg. Or like in this figure it says state, I can use state or q, it's the same thing. And now the next part will be the combinational part in here. And this is what define what the next state is. And this is really straightforward in counters. So let's do that. So we're going to do always, and I'll figure out what are my inputs and output. And it's really, we can say, well, what do I need the next value to be? It's actually, frankly, the current value plus 1. That's what I wanted with the counter. And in here, of course, in the sensitivity list, I need to tell it like when to change. If I don't want to bother figuring out which ones, I can just use a star, and that's pretty much it. Or I know in this particular case, it's just like when the current value changes, I want the next value to be just plus 1. And that's pretty much it for the counter. But of course, because we're outputting q in here, so I need to rename qreg as counter. So technically, I need something with the output logic. In this particular case, it's also a simple one, which is just assign q equals qreg. And that's pretty much it. And now this counter is done. And I went ahead and I wrote assign, let's do this one here, assign q equals qreg. Yeah, this should be fine now. So I went ahead and I wrote the test bench as well, so that we can test this particular counter. So in the test bench, I just created an instance of it. I made it 4-bit, and I ran it for about 200 nanoseconds. And all I did is I generated a clock, and then I issued a reset for about 2 nanoseconds, like we've done before. So I'm going to run this simulation pretty quickly. And now that the simulation is done in here, we can take a look at that. And now the output is, there's a reset for 2 nanoseconds, and that is 0, 1, 2, 3, and it's a synchronous counter, so there's no glitches whatsoever. And as you can see, that the ones that last for 10 nanoseconds, this is 15, and then 25, and then 35, it lasts exactly the same because it's a synchronous counter. So that's how it is. Now, if I wanted to count, instead of going from 0 all the way to 15 and then going back and rotating to 0, we can actually increase it. We can go to the test bench for this up counter, and we can tell it like, hey, I need it to be 5. So it'll go from 0 to 31 at that point. So you run the simulation again, and you can see that this is how simple changing that counter, or the maximum value for this counter. Okay, so after changing that, we'll see that it went 0, 1, 2, 3, and now it exceeds the 15 to 16, 17, and 18. It should go all the way to 31, but it's stopping at 200 nanoseconds because the test bench is written in such a way that it only runs for 200 nanoseconds. Okay, so what if I want that counter to actually count downwards instead of upwards? Well, it's pretty straightforward as well. Instead of adding 1 to the register, for example, I still have the same register. What I'm trying to say is in here is I have the register doesn't change, the output logic shouldn't change, only the next state logic changes. And really, I mean, the change is pretty straightforward. All you have to do is just say, okay, qreg equals now -1, and you just basically move it backwards one by one. However, it's like having an up counter or a down counter is pretty straightforward. Sometimes you're going to see a counter that actually counts up and down. So in here, we're going to create an up-down counter. So we're going to create an up-down counter that actually takes another input called up. If it's asserted, it will go up. If it's not asserted, basically if it's 0, it'll count down. But I also want to show you something else, which is I'm going to add an enable. So the counter that we just built, which is the up counter in here, will continuously non-stop count. Like no matter, like as long as there's a clock, it will count. Like what if I want to stop it for some reason or another? We're just going to add this functionality in here. So we're going to create an up-down counter with a couple of extra signals, an enable and an up counter. And the way we do it is very, very similar to the other one. I'm going to create the registers for me, and then the register should have a reset and so forth. So we're going to do reg, and it's generic, so its number of bits is bits. It's of size bits, and then we do reg and then q next. And then here is for the positive edge of the clock, okay, and the negative edge of reset n, okay. And then we say begin and an end, and now we ask if not reset n, I want the q reg value to be non-blocking assignment 0, or you can say b0. Okay, and then you can say else, and here's usually we do else, well, q reg is equal to q next. But now what I want to do is I want to do it a little bit differently. I'm going to say, instead of else, I'm going to say else if enabled. If that signal is enabled, this is when I want to change the next value. If it's not enabled, I don't want to change it. Okay, that's the only case when I want to change it. Okay, so I just now added an enable signal in here, and it's a synchronous enable, by the way, because it doesn't trigger that always. So this will only happen in the clock signal. So next active edge of the clock comes in, and it's not the reset. So I'm gonna have an enable. If the enable is asserted, I'm gonna give it the next value. Other than that, I'm just gonna stay in this previous value, which I can just rewrite it here. It's not necessary, but it just makes your code a little bit more robust. So we're gonna just say that the next value will be exactly the same as the current value. All right, so this is how we do the first part, which is this one here, which is just the register part or the state. Okay, so next what we need to do is the next state logic, which is a combination logic here. It's next state logic. Okay, in the next state logic, we can do something like this. I usually say, all right, let's figure out later what the always sensitivity list is. And I'm going to start by saying, well, now I have an up-down condition, so I'm going to have to test for it. If up, I want that particular q next to be equal to q reg plus 1, else we can think about it as else or else if, depending on what you want to see. I'm going to just say else q next will be q reg minus 1, and just for the sake of, just in case the if statement or something happened with the q next, I usually say, well, q next, usually we're going to keep it at q reg just in case. So this is just to make sure that we don't get any latches here or whatnot. Of course, you can do star here and we'll figure it out for us. But frankly speaking, I usually take a look at the right-hand side, and the right-hand side, the only thing, and the test as well. So the right-hand side is telling me that if qreg changes, you need to change it, and or up changes, you need to change it as well. So this will take care of the next state logic. How about the output logic? So the output logic is really, because we're outputting Q, which should be the same as QReg. So all I have to do is just assign QReg equal, or Q equals QReg. Okay, and that's an up-down counter. So I've also written a test bench for this up-down counter, and it does pretty much very similar to the up counter. It's an up-down counter with 4 bits, so it should count all the way to 15 or downwards to 0, and then go back to 15. And in here, you're going to see that I generated a clock. And then what I did is I created a reset for a short period of time. I made sure the up is asserted, so it's actually counting up. And then I went and made sure, and I enabled it as well. At the beginning I didn't enable it. Here I put the 0, so it's not reset, or it's reset because the reset is active low, and then it's not enabled. I made sure that it's counting up, and then after 2 nanoseconds I made sure that the reset is now it's basically 1, so it's not reset. So after a couple of negative edge of the clock, I'm going to enable it, and then the count starts, and then I'm going to wait till we reach the final value, and when the final value is reached, I'm going to disable it a little bit. So we're going to keep it for 15 for quite some time, exactly a couple of clock cycles, and then we move the up to 0. That means I want to count downwards, so it starts counting 15, 14, 16, and so forth. So let me show you the result of this test bench. Alright, so here's the test bench. Here's the result of the test bench. As you can see in here, for 2 nanoseconds, I made the reset here to make sure that it starts with 0. And then why don't I just do that here? I'll just put it down so that you get to see it together. So we'll do that in here. So we reset. We made sure that it's not enabled. So this is the enable signal. And after a certain period of time, we enable it and it starts counting. Okay, and then the up is 1. That means I wanted to count upwards, and as you can see in here, from here you'll see it's counting 1, 2, 3, 4, 5 all the way to 15. And then when it reaches 15, exactly when it reaches 15, this is what the weight Q equals 15 is. I'm just going to disable it. So disabling it meaning you're going to keep it at the current value regardless of the clock cycle. We're going to keep it for a while. Then I reduce the up to 0. That means it's counting downwards, and I activate or enable it, and you can see that it goes the way 14, 13 all the way to 0, and then it goes back to 15 and continues as long as I keep the signals as they are. Okay, so the final counter I want to cover is a counter that can count up, down, similar to the up-down counter, and it can also parallel load. So that's what the L stands for. So it's a UDL counter. And if you take a look at the input and output perspective, so it's parameterized, so it has 4 bits. Or by default it's 4 bits, but it can be any bits. And we have a clock, we have a reset, we have an enable, similar to what we did with the up-down counter. Of course, it should have an up signal to decide whether it's counting up or down. Now, the 2 new signals here are the following, which is load, which is a 1-bit signal, and D, which is something to load. It's actually a load signal and the number to be loaded. So this particular counter, you can load it at some time. You can just load it with a number and it'll continue from there. If it's counting up and you loaded it with a 5, the next value would be 5, 6, 7, and so forth. If it was counting down, it'll be 5, 4, and 3, and 2. And of course, the output as usual. So what I'm going to do is I'm going to start with the code for the actual up-down counter. So I'm going to go to the up-down counter in here. I'm going to start, because the code is very similar. It's just a little bit of a change in there. So we're going to do this here. It's actually not copying it. Let me just copy it here, and then do then that, and then here. Okay, so again, that's the beauty of separating it into 3 different parts. So we have the registers. It's pretty much the same exact thing. So the register is activated by the active edge of the positive edge of the clock. If there's a reset, and I have the enable signal, nothing changing here. And the output logic will be the same. So what we're changing is just the next state logic. So let's see. I'm going to just start it from scratch for the next state logic. Okay, so in here, and of course I'm going to just change because the signals will change. Okay, so let's see what we need to do in here. So what we need to do in here is the following. Now, similar to the up-down counter, like I can just continue from the up-down counter, kind of like what we have in here, like another if or something. But I think an easier way to do that will be the following. So let me just remove it one more time. So we can just start from there, and we can say, okay, I want a case. Okay, and the case that I want to test is the following. Actually, I'm going the 2 signals, so control signals I'm looking for, are load and up, and each one of them is a single bit. So I'm just going to concatenate them next to each other. I'm going to say this is load and this is up in here, and then I'm going to say and case in here. So the signals that I care about is actually 2 bits, so I can just say, well, to match 2-bit 0, 0, and then also 2-bit 0, 1, and then I have 2-bit 0, 1, 0, and then I have 2-bit 1 1, and of course I usually have the default, and the default I'll just write it right away. The QNext should be the same as QReg. It might be repetitive after having this, but it's okay. It'll make your code a little bit more robust. All right, so let's figure out what's happening in here. This is 0 0. That means the load is 0 and the up is 0. So I'm not loading and I'm not moving up, so I'm moving downward. So that means the QNext is just QReg -1. It's actually the down counter. Okay, how about this one here? Well, this one here is not loading, and 1 or up is 1. That means we're going upwards. So QNext equals QReg +1. That's what that. Okay, and then of course this one here is actually I'm loading, and frankly speaking, if I'm loading, I shouldn't care what the up value is, whether you're going up or down. The next value QNext should be just the value D, which is the input in here. So I just need the next value to be that way. Of course, I have to repeat the same thing in here with this guy. But I could like basically in the 1 1, if I can say QNext equals D will be okay. However, I'm just going to show you another way, which is basically if I don't care what the up down is, I can just do it that in an X. Now that code might seem to work. However, there's a tiny problem. Or this case statement here is treats X's exactly literally. So it's looking for an up to be unknown, not 0, not 1. It has to be exactly unknown. It's actually literally matching it to X. If it's not X, it's not going to work. The way we treat X as a don't care, whether it's 0 or X, is by using case X. So if you use a case X, and X will be either 0 and 1, and it will basically both of the cases will be matched in here. Okay. And that's pretty much it for the UDL counter, the up-down counter. And as you can see here is like just separating the code with the next state logic in here. It's just a combinational circuit. And from our knowledge of a combinational circuit, I use the case statement. So that's just a multiplexing routing network. It's just a big multiplexer. And that multiplexer is specifically, because its control is 2 bits, it's actually 4 to 1 multiplexer. And that's about it. So I have written a test bench for this particular counter. So let's take a look at the result of this test bench. Well, here's the test bench, but I just realized there's actually a tiny error, and we're going to see it shortly. Actually, let me just correct that error and come back in here. So these ones in here, which is the always statement, I just said it's sensitive to QReg and up. And now I'm using load. If you don't use load, or even D as well, I'm using both of them, you're going to get a tiny error with the load functionality. So one solution is either to add load and I believe D, or I mean it's like an easier way to do all of this so that you don't have to forget like I do. You can just basically say star and it will figure out for us. So I can just save this now and I can run the simulation, and now the simulation will be more accurate. Alright, so here's the simulation result, and what I did is I made the bits 5, so it should count. It's a counter that should count from 0 to all the way to 31 because it's a 5-bit counter. I just instantiated that, ran it for like 450 nanosecond, and created some sort of a clock. And now the stimuli or the test vectors are a little bit more involved because I have different functionalities now. I think it's easier to take a look at the diagram itself to see what's happening. So in the diagram you'll see I'm just resetting for a short period of time, so that puts me at 0. That's the output in here. I'm just gonna change the color so that you get to see it. Maybe I'll put it in aqua, okay, so that you get to see the output of the counter. So in here I'm enabling it at some point. I'm enabling it here, and I'm making up is 1, and it's enabled. That means it should count upwards. So from there you're going to see it goes 1 2 3 4 all the way to, it should go to 31. However, what I'm doing in here is at some point I'm actually disabling it, meaning keep the output as is, nothing will change. And then at some point I'm actually re-enabling it, but I'm putting the up downwards. That means I want it to count downwards. It started counting 15, 14, 13. But when it reached the 13, or like a little bit before here, this is the negative edge of the clock, what I did is I said, okay, I want to load it with a 9. So in the middle of the 13, I said I want to load it with a 9. So I raised the load signal. I put D as the input that I want to load. And then the next active edge of the clock, which is right here, it actually loaded that 9. So it loaded that 9, and now it continues. So it was counting downwards. It will just continue. It's 9, 8, 7, 6, 5, and 4. So it jumped 15 from 13 to 9 because of the load functionality. Okay, and then we go continue, and at some point in here, I'm loading a 7. Okay, so then this is at this active edge of the clock. So it's actually saying, okay, the next active edge of the clock, it will just load it. So you'll see that here is the next active edge of the clock. It will load 7, and it did load 7 and continued 7, 6, 5, 4, 3, 2, and at some point in here you'll see that actually I started moving upwards and I loaded it with an 11. So in here it's 11, so then because I'm moving upwards it's 12, 13, 14, 15, and so forth. Okay, and of course it gets loaded in the next active edge of the clock in here. Okay, and that's how it goes. It's like, so this is here, and then the next active edge in here it stayed at 11. Actually, it stayed, like, I'm looking at it, I was just wondering why is the 11 longer, and I did it on purpose. It's actually an active edge of the clock came in, the 11 and the load were high, and then the next active edge of the clock came in, and again the load is high and the number 11 is at the input. So what happened is started counting in when I actually reduced or deasserted the load, and this is when the count continued. So it's 11, 12, 13 because the up is 1.